Everybody, in this video, we're going to go over the topic from the past week, which was simple two-column proofs and coordinate geometry proofs. So we're going to take a look at this first example. We're going to talk about how you approach a proof and then finally writing it up into a formal proof after we come up with our plan. So first I'm going to take a look at our given information. So I see that BD bisects angle ABC. So I know that the word bisects means cut into two congruent parts. So I'm told here that angle ABC, that's this angle right over here, is being cut into two congruent parts. So I see that the two congruent parts that angle ABC is being cut into is angle 1 and angle 2. My next given says that BC is congruent to CD. So I see in this triangle over here, I have two equal sides. And remember, two equal sides of a triangle, an isosceles triangle, means two equal angles. So I also know that angle 1 is congruent to angle 3. So since angle 1 is congruent to angle 2, and angle 1 is congruent to angle 3, I know that angle 2 and 3 have to be the same. And my goal, I need to always keep my goal in mind, is to prove CD parallel to AB. So I just highlighted the two lines that we're trying to prove parallel, and I'm going to highlight the transversal that intersects them. Notice how we have a letter Z, and in the corners of the Z are our alternate interior angles inside the lines on different sides of the transversal. So angle 3 and angle 2 are alternate interior angles, which is one of our ways of proving that lines are parallel. For this first proof, we're going to write it up entirely together. So I'm going to write it up the same way that we just came up with our plan by taking each given individually, drawing the conclusions that we can from each of those givens, and then moving on to the next given when we're all out of conclusions for that. So statement, reason, chart. So we know, I'll put it in blue because we highlighted it in blue. Segment BD bisects angle ABC. That's given. And from knowing that we have an angle bisector, we concluded that angle 1 was congruent to angle 2. And we knew that because an angle bisector splits an angle into two congruent parts. Then we looked at our next given, which was that BC is congruent to CD. And once again, that was given. And we said that if this triangle has two equal sides, if it's isosceles, that means it has to have two equal angles. So from there, we concluded that angle 1 was congruent to angle 3. And I'm going to put a reason down for that. Our reason was if a triangle has two congruent sides, then the angles opposite those sides are congruent. So once again, in our triangle, we had two equal sides. So the angles opposite those congruent sides were also congruent. And we said that since angle 1 was congruent to angle 2, and since angle 3 was also congruent to angle 1, since angle 2 and angle 3 are both congruent to the same angle 1, that means they have to be congruent to each other. Do you remember what property that is? That says that if two angles are congruent to the same third angle, they need to be congruent to each other. You might be thinking that that is the transitive property. And if you were thinking that, you would be absolutely correct. And now that we know that angle 2 is congruent to angle 3, we know that they're alternate interior angles that are congruent. So that makes the lines parallel. So we're going to end our proof with what we're trying to prove because we now have enough information to prove it. CD is parallel to BA, and I'm going to put the reason down that we just said. If alternate interior angles are congruent, then lines cut by a transversal are parallel. Moving on to this next example, let's take a look together. We're going to do the same process. Take a look at the givens, take a look at what we're trying to prove, come up with our plan. Once we have our plan, then we'll start writing our proof. So it says here that GE, ray GE, that's the symbol for ray, bisects angle DGF. So angle DGF is being bisected. That's this angle over here. So just like in the previous example, we know it's being cut into two equal parts. So I do know that angle 3 is congruent to angle 2. My goal is to prove that angle 1 is congruent to angle 2. Looking at my diagram, I do see that angle 3 and angle 1 come out at the same point and look like they're opposite from each other. That means they're vertical angles, and vertical angles are always congruent to each other. So since we know that angle 3 is congruent to angle 2, and that angle 3 is also congruent to angle 1, it makes sense that angle 1 would have to be congruent to angle 2. So let's write this up. Let me get my statement reason chart ready to go. So first I'm going to start with our given information. Ray GE bisects angle DGF, and that was given to us. Remember our proofs that we start with our given information. That is our basis for drawing all of our other conclusions. And from knowing that GE was bisecting angle DGF, we were able to say that angle 3 was congruent to angle 2. And our reason for that was an angle bisector splits an angle into two congruent parts. Then we talked about how angle 1 and angle 3 were congruent because they were vertical angles, which are always congruent. And we said that anytime we have intersecting lines, vertical angles are formed. So I'm going to write here, intersecting lines form congruent vertical angles. So I want to make sure in my reason I state how I know they're vertical angles, and that's why they're congruent, because they are vertical angles. And then finally, let's think about how we're going to justify our conclusion that angle 1 is congruent to angle 2. Well, we knew that angle 3 was congruent to angle 2, and that angle 1 was also congruent to angle 3. So if angle 1 and angle 2 are both congruent to the third angle 3, they have to be congruent to each other. Do you remember the name of the postulate or property that justifies that? If you're thinking transitive, you are absolutely correct. If two things are congruent to the same thing, then they're congruent to each other. Moving along, in the next example, we're given that AB is congruent to CD. And the conclusion that we need to reach is that AC is congruent to DB. So we're starting with smaller segments, AB and CD, and we're making them bigger to get AC and DB, which are longer than our starting red segments. So since we're going from smaller information to getting information about larger segments, we're going to be using the addition postulate. We're going to add things together to make something bigger. So let me get right to my statement reason chart, and we can start writing down what this addition is going to look like. So my only given information here is that AB is congruent to CD. That's given. Those are our two segments in red, so let me just underline them in red. Okay, so now let's think about what we're going to add on to AB to make the whole segment AC. Well, it looks like we're going to add on BC. Let me write that down. AB plus BC. And here we're starting with DC. Let's think about what we're going to add on to DC to make DB. It looks like we're going to put CB onto DC to make the whole segment DB. And I'm going to write down that that's the addition postulate of congruence. So you might remember that when we're using addition postulate, we have to start with two congruent segments and be adding on two congruent segments. So here we are starting with two congruent segments, AB and DC. We know AB is congruent to DC from the given information, but we don't know that BC is congruent to CB. If we take a look at our diagram, BC and CB are the same segment. So we do know that they're congruent. We just have to actually state it in our proof. So I'm going to say that BC is congruent to CB, or you can write it as BC is congruent to BC. And the reason for that is the reflexive postulate, because anything is congruent to itself by the reflexive postulate. So now we've justified our addition. That will be our step 3. And then we know we have to end a proof with the conclusion that we're trying to reach. Let's think about how we can justify that conclusion. AB plus BC, if we put AB and BC together, that makes AC. DC plus CB, if we put those two segments together, that makes DB. So we're replacing the addition with the segment that means the same thing, with an equivalent segment. The substitution postulate says that we can replace something with something else that is equivalent. Okay, so this one can be done two different ways. It can be done with the subtraction postulate, but that's not how I'm going to do it. I will talk about that before I end this proof at the end. So angle ABD and angle CDB are right angles. Angle 2 is congruent to angle 4. We need to prove that angle 1 is congruent to angle 3. So I could use subtraction because I have the whole 90-degree angles. If I subtract off 2 here, I'll get angle 1. If I subtract off 4 here, I'll get angle 3. But that's not how I'm going to do it. I'm going to use the fact that angle 1 and angle 2 together make 90 degrees, so they're complementary. And that angle 4 and angle 3 together make 90 degrees, so they're complementary. So here I just started writing my proof. I put down my given information, my two pieces of givens, and then I just wrote down that angle 1 and angle 2 are complementary, as well as angle 3 and angle 4. And we know they're complementary because angles that form a right angle are complementary to each other. So since I know that angle 1 and angle 2 are complementary, and angle 3 and angle 4 are complementary, and since angle 2 and angle 4 are congruent, I know for an absolute fact that angle 1 needs to be congruent to angle 3. And just for all purposes, I'll get rid of the measure and I'll change this to congruence so it's less confusing. So angle 2 is congruent to angle 4. There we go. So angle 1 is congruent to angle 3 because complements of congruent angles are congruent. So once again, angle 1 and angle 3 are both complementary to congruent angles. Angle 1 is complementary to angle 2. Angle 3 is complementary to angle 4. And angle 2 and angle 4 are congruent. So since angle 1 and angle 3 are complementary to congruent angles, they must be congruent as well. Once again, the complements congruent angles are congruent. I want to also remind you again, you could have used subtraction. The big 90-degree angles, subtract off angle 2 gives you angle 1. Subtract off angle 4 gives you angle 3. The subtraction would have also worked, but complements of congruent angles are congruent, does it in less steps. Okay, here we have a coordinate geometry proof. So that means we're going to be using formulas and calculations to prove what we need to prove. We know that we're not writing a 2-column statement reason chart because I see coordinates in the question and I just see a grid here. So remember, our steps are formulas. Write down your formula, show all your calculations, and then end with a concluding statement, which is a sentence summarizing what your calculations are showing. So here I just have triangle SU graphed, and part A tells us that we need to prove that it's a right triangle. So remember, a right triangle has a right angle, and a right angle is formed by perpendicular lines, and perpendicular lines have opposite reciprocal slopes. So if we can show that two sides of this triangle have opposite reciprocal slopes, then we'll know that the sides forming them, for example, this side and this side, are perpendicular, meaning they form a right angle, making it a right triangle. So you can do the slopes on your own, pause the video. I'm going to do the same as. And after doing the slopes, I can see that side SU and side UE do have opposite reciprocal slopes. Notice how the slopes are the same. One's just flipped over, the reciprocal, and with different signs, the opposite reciprocal. So I do know that this is a right triangle. So I'm going to put my concluding statement. So triangle SUE is a right triangle because two sides have opposite reciprocal slopes, meaning they are perpendicular, and perpendicular lines form right angles. Part 2 says to show that triangle SU is not an isosceles right triangle. So an isosceles triangle has two congruent sides. So now we're trying to show that SU does not have two congruent sides. When we want to find the lengths of sides, the formula that we're going to use is distance formula. So you can pause the video and you can find the lengths of the side of the triangle. I'm going to do the same thing as well. As you can see here, I did all of my distance formulas for each of the three sides for SU, UE, and for SE, and I found that all of them were different lengths. So I ended with a concluding statement that explains what my calculation showed. Since all three sides are different lengths, triangle SU is not isosceles. And if you don't end your coordinate proofs with a concluding statement explaining what your calculation showed, you will lose points. It will lose points on your test in your geometry class and also on the Regents exam. So make sure you always end with a concluding statement explaining what your calculations show, and make sure you do always show all of your work in order to get full credit. Here's another one. We need to show that XM is the perpendicular bisector of YZ. So perpendicular bisector is a two-part word. Perpendicular, we know that we can use slope formula for that. We can show that we have opposite reciprocal slopes since perpendicular lines have opposite reciprocal slopes. Bisectors cut segments equally in half. So we know that they pass through the midpoint of a line segment. So we can find the midpoint of line segment YZ and verify that it is point M. So I'm going to pause the video, do it as well. Find the slopes of XM and YZ and see if they are opposite reciprocals of each other. And then find the midpoint of YZ and see if it actually is point M to verify that this is in fact the perpendicular bisector of YZ. Here I have my calculations. So I found the slope of xm and the slope of yz, and I found that they were opposite reciprocals of each other. 1/3 and -3 are opposite reciprocals, different signs, the fractions are flipped. So the perpendicular part is covered. And then I found the midpoint of yz, and I found that the midpoint of yz is the 0.44, which is point M. So I ended with a concluding statement. Since xm and yz have opposite reciprocal slopes, they are perpendicular. Since the midpoint of yz is point M, xm bisects yz. So xm is the perpendicular bisector of yz. Please take a second and pause the video and read the question. The question is saying that Owen says the median from point E must pass through point G. And we need to verify if Owen is correct and explain why or why not. So we need to remember what a median is. So a median is a segment in a triangle that connects a midpoint to an opposite vertex. So if it's going from point E, that's a vertex of the triangle. So it should be going to the midpoint of the opposite side. So if it was going to pass through point G, G would have to be the midpoint of side DF. So what we need to do is we need to verify, is point G actually the midpoint of side DF? If it is, then the median is going to pass through point G. If it's not, then the median is not going to pass through point G. I'm going to pause the video so I can find the midpoint of DF. I recommend you do the same. So when I found the midpoint of DF, I found that the midpoint of DF is the point 5/2, 1/2. That's not the coordinates of point G. Point G has coordinates 1, 2, 3, 1. So I'm going to write a concluding statement that says Owen is not correct. So here I wrote my concluding statement, and I'm hoping that you paused the video and wrote your own as well. No, the median from point E would pass through the midpoint of side DF, which is the point 5/2, 1/2. Point G has coordinates 3, 1 and is not the midpoint of DF.